Hey guys, what's up? So today I want to introduce you to a very important topic in calculus called linear approximations, okay? Now this is a very helpful way in which you can apply differentiation into, approximations, and you can do many things in math that are very helpful using linear approximations, okay? So now we're going to begin by showing you what the notion of a linear approximation is and where it comes from, okay? And some basic conditions that you need to keep in mind when playing with these approximations, okay? So let's begin. Now, every linear approximation is founded on the idea of a derivative and on the idea of a slope. So remember that you can compute a derivative. We're going to say f prime of x. We know that is going to be equal to the limit as, let's just say, delta x approaches 0 for the function f of x plus delta x minus our initial point, which is going to be f of x, okay? We're going to divide this whole thing by delta x. Now, this is the definition of a derivative, and you can also write this as the limit as delta x approaches 0 for the change in f. When you take this subtraction, that is going to be the change in x. How much did f change to get from f of x to f of x plus delta x, okay? This is going to be the change in f. And we're going to be dividing by the change in x, okay? So now this would also be the definition of a derivative. And to get to the notion of a linear approximation, we need to remove the limit notion, okay? Because we're going to say that the derivative of any function, f, is going to be approximately equal to the change in f over the change in x, okay? Now, see that I didn't write equals because we removed the limit, okay? When we're using the limit, remember, we're starting to play in infinitely small scales. But if we don't include the limit, well, this is going to be a fraction that is going to have, well, numbers that are relatively big if you compare them to what a limit would give you, okay? When we say limit, we're basically saying that delta x is approaching, is infinitely small, okay? Which is basically 0. And in this case, we're saying that delta x is any number that is, is tangible, okay? So in this case, we do not include the limit, so we need to use this sign. Now, a linear approximation, its goal is going to be to use a linear function to estimate the value of a function at a particular point, okay? So now, how can we derive an equation that does that from this expression? Well, let me show you something. You can move delta x to the other side, and then you can multiply. So you're going to have f prime of x times delta x. It's going to be approximately delta f, okay? And now you know that this would be the same as if you had f prime of x times x minus x naught. So x naught would be our base point, and x would be, any variable that is moving. You can choose how much x is depending on the function that you need to estimate. And x naught, I'm going to show you the relationship between these two in a better way in just a moment. And this would be approximately equal to the change in f. We know f would be f of x. The change in f would be f of x minus f of x naught, okay? Now you can see that this is the exact same idea that is represented by this equation in here. The derivative is going to be the limit of the change in f divided the change in x, okay? But now what if you take away the limit? Well, now you cannot say that it's equal to, that the derivative is equal to this expression, but that is only approximately equal to, okay? And so you get this expression over here by rearranging and playing the algebra. And now the typical formula that you have, that you've learned about linear approximations or that you may have seen out there, is as follows. So you have f of x naught. You just simply move this term to the other side, plus the derivative of x times the change in x, and this would be approximately equal to f of x, okay? Now this is the typical formula for linear approximations, okay? So we basically say that any function that you have, you can approximate it by this expression. Now there is something very important about x and x naught. Since we derived this expression from the notion of a derivative, well, x and x naught, they need to be pretty close, okay? Now, depending on the context, you define what pretty close means, okay? Depending on the problem that you're solving, being close means something totally different, so that's up to you. but x and x naught, they need to be close, okay? You cannot have x being equal to 100 and x naught being equal to 1 if you're doing, I don't know, something that deals with the small values, okay? Because then this approximation would not work. And that happens because we derive this expression from the idea of a derivative. Now, a derivative uses 2 points that are very close to each other. But if you grab 2 points that are very far away from each other, then this statement no longer holds, okay? Because you destroyed the requirement that a derivative is 2 points that are very close. And if you move those points away, well, then you no longer have a derivative, okay? You have basically an average rate of change. And that doesn't work out if you're taking a linear approximation. You need to make these 2 points be close to each other, okay? Because this idea comes from a derivative. And a derivative uses points that are close, okay? That's the main idea behind why you need these 2 points to be close. Now, usually we say that this approximation works for x values. So this approximation works for x values near, so you can say near x equals x naught. And now this allows you, this statement allows you to do something pretty cool with this expression, and it's that every time you're playing with this expression, you can basically interchange x and x naught at your convenience, okay? So say, I don't know, say in a problem you were given the value of f prime of x naught, and you cannot find the derivative of f prime of x when x equals any number that you want, just because, I don't know, the problem makes it that way. You cannot evaluate the derivative at any point, but you can evaluate the derivative at x naught because the problem gave you that information. Well, instead of writing that this approximation uses f prime of x, you can write that this approximation uses f prime of x naught, okay? That is something that you can do. So you can interchange x and x naught at your convenience, depending on the problem, okay? That is a very important technique to solve problems using these approximations, okay? So now I think to finish all of this, I'm gonna give you a small example. I'm gonna give you, let's say sine. So we're gonna approximate or linearize, that's the word we use. We're going to linearize the function sine using this approximation over here. So I'm gonna do that over here. So I'm gonna say that sine of x is gonna be approximately, now f of x naught, let's take this approximation near x equals 0, okay? So I'm going to say this is near x equals 0, which means that x naught equals 0, okay? So now how much is sine of x naught, that is sine of 0? We know that would be 0, so I'm going to write it so you know that there was something in there, which was this term. Now what is the derivative of sine, which would be f prime of x? Well, we know that would be cosine. X equals 0. So now how much is cosine of 0? We know that's 1. So we have 1 times the change in x. So I'm actually just going to write change in x for now, and then we can substitute the values. And this would be approximately equal to sine x. Now, there is something pretty nice, and it's that we can continue. I'm going to continue in here. So we can say that sine x would be approximately the change. So this would be x minus x naught. Okay, and the parentheses you don't need it, but I just wrote it. So now, here comes what I said about being able to interchange between x, being able to interchange x and x naught. Since you have this expression, well, this expression is actually not equal to 0. If you think that you can do 0 minus 0 because we have this information, nope, that's not the case. You can say that that sine of x would be approximately x minus 0, okay? In this case, you can assume that x is any fixed number that you want. It's any number that you're evaluating the function sine at. And then x naught, well, we know that would be our base point. And in this case, well, you can just say that x, you have the freedom to say that x is going to be the variable. You're not going to assume that it's x. And then, well, you can say that x naught equals 0, okay? Because that was the base point that we used. We said that this approximation works for values near x equals 0. So you can say that x naught equals 0, and then you just simply get that sine of x equals, well, it's approximately equal to x for values very close to 0, okay? And now that makes a lot of sense because if you remember the sine function, well, at the origin is going to have kind of on a slope that is approximately, let's say it would be something like this. Let's say it would go something like this. Close to the origin, the sine function, well, it follows the behavior of a linear function with a slope of 1 and a y-intercept of 0, okay? So now you can see this approximation only makes sense for values close to 0, okay? And now this is what we call the small angle approximation. I'm pretty sure you may have seen some memes before about this approximation, which works out for very small numbers, and anything you know that is considerable, that is tangible, any number that is kind of large, it's not gonna work out. Oh, sorry, it's not gonna work out. You're not gonna be able to compute it using this approximation. But for any number that is, well, decently small, this will work out, okay? So I believe this has been an introduction to linear approximations. This is a pretty interesting topic because there are many ways in which you can use linear approximations to solve many things in math. Remember, a linear approximation allows you to represent any function f of x, anything that you want in terms of a linear function, okay? You have a y-intercept and a slope, and then your input variable, okay? And now that is something very powerful to do in math, because many times you want to write a function that you have in terms of something that is simpler, okay? And there's no simpler function than a linear function, okay? So yep, that has been everything. I hope that you learned something. I hope that this information has been valuable. And yep, see you in the following video. Bye.